Good morning, everybody. There we go. So it's very exciting to be here in Israel. It's my first time ever in Israel. I've actually planned a full day of sightseeing tomorrow to get to know the area a little bit while I'm here. And it's also very exciting to be here keynoting and kicking off the first ever BlueHat Israel. It is, I understand there's about 400 people here, making it the largest inaugural BlueHat Israel in history, period, which is, it's very exciting. Now, what I'm going to talk to you about this morning is to share with you a look at how we're pushing the boundaries of using machine learning in cyber defense at Microsoft. I gave a talk at RSA conference back in February about how we use machine learning in cybersecurity at Microsoft. How many people saw that talk, just out of curiosity? So that's pretty disappointing, actually. But good, so I can reuse a lot of the same content, which is fine. Just out of curiosity, how many of you are using machine learning in some way or another in cybersecurity today already? So a handful of you are already pioneering. Well, I'm here to tell you that I believe that cybersecurity is the future, or machine learning is the future of cybersecurity. And the work that's ongoing here, which I'm going to share with you a little bit of, is just the first steps I see, the nascent steps really, in how we can apply cybersecurity to disrupt attackers. Now at Microsoft, we are using machine learning everywhere, and this is what's spurred us to try to push machine learning into the way that we address cybersecurity. If you take a look at all of these products and services here on this slide, all of them either enable people to develop machine learning algorithms, to run machine learning algorithms, or machine learning algorithms are part of the very operation of the service. If you use Xbox Live, machine learning is sitting there figuring out how to match you with other players when you play online. You use Cortana. It's using machine learning, of course, for speech recognition. And then we have our cognitive services, which allow you to call our speech recognition APIs and visual recognition APIs that are built on top of course, machine learning. So over the last few years, we've tried to figure out how to get machine learning to improve the posture of our cyber defense systems. And if you take a look at the kind of scale that we operate at Microsoft across our services, it's a massive scale. There's tens of petabytes of log data being spun off our systems every single day. If you just take a look at logins, one aspect of security, the authentication process, we have over 1.3 billion authentications every day in Azure Active Directory and 300 million users in our Microsoft account systems. Now, our early application of machine learning and other security defense mechanisms have allowed us to defend our infrastructure as well as our customers. You see the number of security defense operations that we have every single day on an automated basis. 10,000 location-detected attacks using our identity protection systems in Azure Active Directory. That's one of the places we apply machine learning, and I talked about that in my RSA conference talk. And then we detect 1.5 million compromise attempts by attackers as well, and then alert users or use automated prevention of those. The challenges, though, is that detection isn't enough when it comes to using machine learning in cyber defense. We've got to disrupt the attackers, and it's not just enough to have great detection. You need to shorten what's called the kill chain for defenders. Now, what's the kill chain? A lot of you are familiar with the kill chain for the red team or an attacker here, which starts out with performing reconnaissance, establishing a presence, moving laterally, escalating privilege, and then exfiltrating data ultimately, typically is the goal of the attacker. Well, the blue team also has a very similar type of kill chain, fighting against the red team. It starts out with gathering information about what's going on in the system, detecting potential malicious activity, generating alerts, triaging those alerts to see which ones are false positives and false negatives, establishing a context and a plan, and then executing on that plan. So disruption in the context of the blue team kill chain means changing from an attack detection mentality to an attack disruption mentality, which is pulling back the tail of that kill chain. And once you pull back the tail of the kill chain, you can start to cut off the attacker's kill chain. The sooner that you can take actions based on some evidence that you've picked up about what the red team's doing, the sooner you can cut off their ability to get all the way to the end and their ultimate goal, which is going to be exfiltrating data. But there's a number of challenges facing attack disruption. One of them is false positives, and the other one is manual triage. Let's talk a little bit about the false positive problem, which I'm sure everybody in the room is very intimately familiar with. This is one of the banes of cybersecurity, is all the noise in the system. And the fact is that false positives kill your ability to disrupt the attacker because you lose the ability to triage. You lose the ability to triage simply because there's too many alerts to triage. And so you have this challenge of figuring out which ones are the important alerts and which ones are the non-important alerts that I can ignore. And many of the cyber breaches we've seen in the last few years, there's been alerts, but the fact is that the defenders have not processed them because they've been overwhelmed with all of the noise created by the false positives in the system. And one of the first steps that we took to try to address this with machine learning is to automatically gather all the evidence around an alert, and then in the alert itself allow the defender to go and access that supporting material and even do things like go take a look at the graphs to show them, hey, there's an anomalous event here that we're going to alert on. Here's how you can look at across all the events to see if it's truly a true positive or a false positive based on the other patterns. Now, the fact is that even this is just too overwhelming for the defender. So this was the first step, but it's not sufficient. And when it comes to really addressing false positive, we have to change from a kind of statically defined system, which has been traditional approach in cybersecurity, especially in the anti-malware business, which is to write a program that takes in rules. It's basically rules and then the data and produces an output. It's whether this thing is malicious or not malicious. The challenges with this are the false positive problem because the rules are very rigid. Not just the false positive, but the false negative problem. And if you match the rules too broadly, then you're generating lots of false positives. If you match it too narrowly, you're letting the attacker through. The idea behind taking machine learning and applying it in an attack disruption model is to take advantage of the fact that machine learning is a learning system. The way that you generate the program itself is to take a bunch of data, take a bunch of labels, and I'll talk more about what labels are in a second, but once you have labels that say whether things are good or bad, and train it against a set of data, then you can produce a program or a model that then you can give new data, and that model then has been trained to identify and separate the good from the bad. And the benefits of this is that it's dynamic. It's not rigid. And the more effective the labeling, the more effective the output is, the more accurate it is. So our goal is to get very, very accurate with the labeling of the data. Now, at Microsoft, we've got a kind of an unfair advantage against attackers because we've got so many sources of labels, so many sources of true attacks that we can label all of the evidence, all of the alerts, and say these are really parts of real attacks that we've determined. Things like our red teams themselves, which are constantly attacking our systems. And those red team activities are generating a lot of alerts that we can go look at, triage, and classify if they haven't already been classified automatically as true incidents, true breaches that then get fed into the machine learning algorithms. We also, of course, have our threat intelligence systems, Microsoft Security Research Center, where we're getting intel from other companies. We've got our own domain experts in machine learning and cybersecurity that are going and labeling data. And then we've also even got automated attack bots, which are constantly performing automated attacks of our systems and generating incidents that then are labeled as the result of knowing that they came from the attack bots. And all of this is great, rich food for our machine learning algorithms. Now, the other problem, though, that we also have with attack disruption and reducing the kill chain is the manual triage process. The fact is that when we do have one of these alerts, that the security responder has to go and then triage it. And no matter how good the system is, there's always going to be the cases where there's false positives that get through. And so the security researcher has to be equipped to go and triage, not just triage, but analyze and figure out a response to what's happened. And there's been very little intelligence so far placed on this end of the spectrum. So what I'm going to talk about a little bit later, towards the end of the talk, is how we're even trying to figure out how to apply machine learning to the triage process. Now, before I get into some of the examples of how we approach attack disruption with machine learning algorithms, with a couple of examples that I'll go a little bit deep into what the machine learning algorithms are, how we label the data, and then what the effectiveness of that is compared to the traditional methods, let's talk about what is an effective machine learning solution. And it's really represented by this pyramid here with at the core successful detection. And the fact is that a successful detection needs to be adaptable, needs to be explainable, and needs to be actionable. These are what we aspire to, the goals that we aspire to as we look at machine learning applications in cyber defense. Now, what I'm going to go ahead and tell you up front is that we haven't fully achieved all these things. We're heading towards them, and this is what I think makes this field so exciting, is because we're just at early stages and there's so much more innovation to do in trying to have machine learning solutions that achieve all these goals. Now, let's talk a little bit about what I mean about adaptability. And adaptability is extremely hard. These rule-based systems aren't adaptable. And when you have a cloud environment, you absolutely need adaptable solutions. Why? Because, first of all, the landscape, the threat, the attacker's targets are always changing. We're always updating services. We're always releasing new features. We're releasing new services. And all of this, it means that as we analyze the data coming out of the system, it's always different. Every single day looks slightly different than the day before. And if you take a look a month to month, drastic differences in the patterns of data that's coming out of those logs. And then when it comes to the labeling and automatic classification of what attackers are doing, that's also changing as well, because attackers are changing their attack patterns to adapt to the changing targets. When a new service comes out, the attackers go figure out how to attack it. And then that's new types of labeled data that we've got to look at, real attack data that we've got to look at and figure out how to classify. And then explainability is something that we also strive for in machine learning. When you have an alert come out that's based off of machine learning, what a responder wants to figure out is, why did this alert get generated? What made this interesting? And one of the problems that we've traditionally had in the space is that if you take a look at what machine learning produces for a responder, it's oftentimes the scored data across a bunch of different features, summarizing up into some aggregated score that is supposed to be representing just how important this thing is, or how likely this is a true positive. So some number between 0.2 and 0.9, and the responder looks at the 0.9, might look at a few 0.9s, and then the question is, which of those are really things that I should go prioritize? Because some of these might be false positives, even if they've got high scores. Why did the machine learning algorithm make this a 0.9? And if I knew that, maybe that would help me prioritize what I go after. When you look at a chart like this, it's impossible to tell what's important and what's not important. It's just a bunch of numbers. So we strive for machine learning algorithms to give the responders more information for them to go and perform their triage. We'd also like for the detections that are being produced by the machine learning algorithms to all be actionable. So there's no good in a detection or an alert where the responder just doesn't know how to deal with it, where there's no prescriptive guidance and they've got to go figure it out themselves. It'd be better if the alert said, hey, here are the steps you should take. Here are some possible mitigation steps to go and close down this vulnerability, or kill this attack, or get the attacker out of your system. Some examples that might be actionable, recommendations on policy changes. Hey, go firewall off this port that's sitting out in the open, which is something that the attacker used to move laterally. Or go reset the user password on this, because it was clear that the attacker has access to it as they move laterally through your system. Those are actionable results of a detection, and it'd be great to have that surfaced up at the time the alert comes through from the machine learning system. So with that at the core, though, we have to come up with an effective detection system. And we look at it through the lens of a framework that I've got here described in graphical form. There's 3 dimensions of a successful machine learning detection framework. Across the bottom is the sophistication of the algorithms that you're using in your machine learning system. And then on the left, you can see the security domain knowledge that you're actually applying to those algorithms. And on the right side, the usefulness of the alerts that get spun off as a result of the combination of those things. Now, in a traditional kind of system, which is anomaly-based or an outlier-based detection system, you're basically looking for things that stand out from the normal. and you might generate alerts off those. And one of the very common ways to do this, if you just take a look at one domain like potentially anomalous logons, is just to look at those outliers in terms of the rate of logons on a particular account. If the rate goes up, we set a rule that says if more than n logons in this amount of time, generate an alert, because that's probably suspicious. That's the most basic kind of rule-based system that you'll see when it comes to anomalous logon detection. The problem with this is that you've got a basic algorithm, which is great. There's no domain knowledge in place. And what that means is that you're going to run into a lot of noise. Like, for example, when the password gets changed or expires, you're going to see a bunch of new logons as the user from various locations is logging on, maybe using the old password, figuring out that they need to apply the new password, or the credentials are cached and they start to fail. And so now you've got these alerts that are just really part of normal operation, but now they become false positives and noise in the system. So what you do at that point, a lot of people do at that point, is they bring in their machine learning experts and some domain experts to go and tune the rules. And they'll set the rules up and create more complicated rules to try to identify those true anomalies, those ones that are more likely to be false positives. And some of the rules they may layer on are like, hey, on weekends, there should be fewer logons. If there's the same rate of logons or higher on the weekends, then let's go generate alert. And you can imagine all sorts of other tweaks and tuning rules, and you end up with this whole conglomeration of a bunch of rules that summarize up into, is this thing truly an anomalous logon or not? The problem with this is now you've got more complexity, but you really haven't made the thing more useful. And in fact, in a global system, a rule that is based on weekend logons, where users are traveling all around, like I'm in here, Israel, and what is the weekend for me when I'm kind of off in US time or Israel time and I'm logging on at different times, that starts to become false positive noise, especially if you take a look at this kind of scale of thousands of users running around the world violating these assumptions around what's the weekend. Now that starts to fail as well. So you got a lot of complexity, but it's still rigid. So what we want to do is have true algorithms that learn, and to have machine learning experts and security domain experts working together to get labeled data, which are that data which is, these are true anomalous logons based on what the red team's tried to do or based on what an attacker outside has done. And what we do is we can take all of that data that we've got that's labeled, meaning we've got a whole set of data. We know for fact that this part of the data is true malicious activity, and then we go train a model, an algorithm. Now produce that model, and now we can take data from tomorrow, plumb it through that algorithm, and it will then, because it learned what bad looks like, start to tell us badness in that new set of data. That's our goal, and that's continuously adaptable. And what you do is you always are relabeling and generating new labels because the system's adapting. So this is not a static thing. This is not something where you just set up the rules, or set up the model, train it once, and let it go. You need your domain experts to be, and your machine learning experts to be constantly tuning this thing. But it's much more flexible and much more resilient than the rule-based system. And it's much better at figuring out what a true positive and a false positive looks like. So these are our goals. Now what I'm going to do is walk through with you a couple of examples of how we're applying machine learning that I didn't talk about last RSA conference, and go deep into the algorithms. Again, the goal here would be to disrupt the attackers, to be actionable, to have some kind of explanation, and to fit that framework where we've got domain knowledge and labels that are constantly making this thing better. In this first case study, the problem is that we want to detect compromised virtual machines in Azure. And there's customers that get their virtual machines compromised because, for example, they've left firewall ports open, they've got RDP weak passwords that have gotten in, or somebody's gotten in through their on-prem network into their Azure virtual machines. They've compromised something there and then moved laterally into the cloud. They've got software that's unpatched, and that lets the attacker in. So there's lots of cases where the machines are compromised. Now we want to detect these things. How do we detect a compromised virtual machine? And that's a tough problem. But one of the advantages that we got in the cloud is that we can see all the network activity that a virtual machine's performing. So our premise is, what does a compromised virtual machine's network activity look like? And by the way, one of the advantages of this networking traffic that we get off these virtual machines is that it's OS agnostic. The customer can't turn it off. It's just there for us to analyze and to try to get insights out about what's compromised and what's not compromised. But how do we classify malicious virtual machine networking activity? That's the question that we're posed. And we came up with an idea, which is one of the fundamental signs of a compromised virtual machines. In many cases, attackers compromise a virtual machine, and unless it's a targeted attack, they're using it as a platform for malicious activity, general malicious activity. One of the most common platforms uses is sending spam. So what if we can figure out what a virtual machine that's sending spam, what its networking activity looks like, and then we can go look at virtual machines' networking activity and then identify ones that look like they're sending spam, and then those are ones that are potentially compromised. The challenge is that not all virtual machines that are sending email are spam. So how do we figure out which ones are sending spam or not? And this is where we leverage some of the assets that we got at Microsoft, which is lots of different services that we can go and get data sets and labels from different services and cross-apply them. In this case, we realized that, hey, well, you know what? We've got Office 365. Office 365 is a fantastic source of labeled data for spam. Lots of, even end users are labeling the data for us. We're labeling the data ourselves. Other outside parties through our threat intelligence networks are labeling the data and letting us know. And then end users are saying, hey, this thing is spam. And we can see in those emails that are labeled as spam the IP addresses. And then we can go intersect those IP addresses against the IP addresses of our Azure virtual machines, and we know that those are now compromised virtual machines. That's the training data, the label data that we can apply in machine learning algorithms. And by the way, I just had to share this with you. This is a screenshot of customers. There's no customer PII in here, but this is a customer's directory of one of their virtual machines recently. So I don't know if you've heard, but ransomware has become popular in attacks on big data systems. There was a Mongo vulnerability that's been attacked recently. But this is a Hadoop cluster that a customer had. And you can see the attacker left an interesting note there in one of the files. Kind of a, yeah, I got you, but by the way, you should get your stuff together. No data for you, secure your stuff, is the message. So attackers with a sense of humor, always good to see. So let's talk about this technique in a little more detail. How do we take that labeled spam IP addresses and combine it with the IPIFX data that was coming out of Azure Virtual Machines and then train the algorithm? We train the algorithm, and now once we've got that trained algorithm, we can take new data, IPIFX data, plumb it through the model, and then come out with a yes or no, this virtual machine looks like it's compromised based on that. This is going to catch not just machines sending spam, by the way, but even likely other machines that are acting maliciously, but in a spam-like way. So let's take a deep dive now at that machine learning algorithm that we're using. It's a weak learner model. And how many of you work with machine learning directly yourselves, have a background in this? Okay, so quite a few of you. In this system, what we want to do is take the training data, run it against the model, this weak learning model that tries to classify things accurately, and then see what the results are. So here's the input data. Those pluses are the incidents that should be labeled as spam, for example, and the minuses are ones that shouldn't be labeled as spam, or vice versa, however you want to pick it. It's just a binary system. We want to classify the set correctly. And the result of that first learning phase, that weak learning pass, might look something like this, where the learner has classified correctly the 2 pluses on the left, but misclassified the 3 pluses on the right side. It's classified those as negatives rather than positives. So it's not a perfect algorithm. So what we do is to train the algorithm again, run another pass, we emphasize or upweight those ones that it classified incorrectly and downgrade the ones that it classified correctly. And what that does is make it try to optimize the learner to go correctly classify those ones that the first learner misclassified. So here's the upgrade and the downgrades. We rerun the learner, and now in this second phase, this second learner gets it more right, but also gets some wrong as well. So it's now correctly classified those 3 pluses, the positives that the first learner missed, but it's also in the process been a little over aggressive, and those negatives have been misclassified. So not perfect either. So we run the iterate algorithm again doing the same thing of upweighting and downweighting, boosting or deprioritizing. And then this third learner might look something like this, where it also misclassifies some, but it correctly classified those ones the previous 2 learners didn't classify correctly. And now what we've got are 3 learners. They're all imperfect, but we can combine the results and now get a learner that actually, or a result that actually correctly classifies everything. And so you can imagine this being done thousands of times with thousands of different learners all combined together, each one not perfect, but the sum of them being highly accurate. And that's what we do when we look at these spam data in the IP addresses. And the data that we're using, by the way, in this case are, of course, the net flows here, the source IP address, destination IP address, number of TCP flags on the connections, the number of connections per hour or per second. All of this is fed through into this, and with the labeling that determines whether it's spam activity or non-spam activity. And the results of this, you can see, we process about 360 gigabytes of data per day and train the model on a regular basis. And that model training, again, because of the cloud scale, and John Lambert here is going to talk about cloud scale and how it can help in defense tomorrow, means that we can go and train those learners in just a matter of minutes. Now, the scoring is typically much more efficient than the training, and you can see that the scoring, which are running continuously all day long, just takes a matter of seconds. So when we see new set of network activity, we can go and then classify that as spam or non-spam activity, compromised or non-compromised VM activity, just in a matter of seconds. And you can see going just from only using Azure's data to try to figure out, using rules, whether something is spam or non-spam, you can see that our effectiveness rate was about 55%. When we started to apply machine learning by using the labeled O365 data, we got that detection rate up to 81%. So a net 26% improvement in our ability to correctly classify a virtual machine as being compromised because it's exhibiting spamish type network activity. So I think this is and as far as actionable, this is actually an alert that a customer will see when VM's network traffic looks like it's potentially malicious. And you can see that this says network traffic has detected suspicious outgoing activity, it could be spam. And then we actually even have recommendations on what the attacker or the defender should do. Like install and run Microsoft's malicious removal tool. And these next two, I think I love. I didn't realize this until I was looking more closely at this slide a little later. Install auto runs, fantastic tool. And run Process Explorer. Now, I don't think most users know how to use Process Explorer, but nevertheless, this is fantastic guidance in my opinion. So that's an example of applying machine learning for attack disruption and helping customers. Interesting thing about that, combining two disparate data sets from two different sources that we've got across our systems. Now, this next case study is also interesting. This one is how do we detect malicious attachments? And as we know, that rule-based anti-malware is very fragile. It's not adaptable, and there's lots of false positives and lots of false negatives that come out with it as well. We'd like to do better, see if we can do better using machine learning. And the hypothesis is that if we take the hard logic of those rules and we combine it with the soft logic of machine learning being trained on real attacks, can we do better as a combination? Just take advantage of the rules because the rules are there and they're going to be updated by the community and by us, but then augment it with dynamic systems that are learning about malicious activity and then maybe even detecting zero-day malware that's similar to existing malware systems or attacks, but is not known by the rules at all. What does that look like? The solution that we've come up with and that we're productizing right now, putting into production right now, is to build two machine learning models. And I'll talk a little bit about both of these models here in a minute. The first one is a model that baselines malicious behavior. It takes a bunch of data about the way that the malware behaves and sets up baselines, and then uses those baselines to go and look at new attachment behavior and determine if it's potentially malicious or not. And the second one is more of one that takes the rules in as features, also with taking advantage of the dynamic behavior that we witness. And I'll show you in just a second what I mean by observing the dynamic behavior of malware. And then combine those two machine learning algorithms together and then come up with that. So it's taking advantage of the rules, but again, soft programming and adaptability of watching a live system. Now, how do we watch a live system in Azure with email attachments? Well, this is actually part of a feature, Advanced Threat Protection Service, that customers can sign up for, where they can choose to have email attachments that go to their end users in Office 365 automatically get scanned to see if they're malicious. And you can see this pipeline flow here. There's a few things that this system does. The first thing, of course, it does is just runs it through a number of antivirus engines. And if the antivirus engine flags the thing as malicious, well, then automatically it's going to be stripped, and the end user is going to be notified, hey, this thing is malicious. But what about the zero-day malware that the anti-malware says looks fine? We'd like to also catch malicious attachments, the PDFs, the docx's, the flash attachments, the exes, that the anti-malware is not aware is malicious. And, of course, there's new malicious files and attacks coming out every day. Let's see what we can do with those. So let's go watch how those attachments behave. What would happen if the end user opened them up? And to do that, we create a detonation chamber system. This is detonation as a service, we call it, which is we send the attachment off to the service, and then we open it inside of a virtual machine. This virtual machine is a fresh, clean virtual machine. It's got a whole bunch of monitoring systems inside of it, which I'll talk about in a second. And then we watch what it does. So that process of getting into that virtual machine, we do 3 phases of analysis. There's one, a static phase, which is just to do hashes of the image. So we do the MD5 and the SHA-1 and the imp hashes of it. We analyze it with the PE analyzer to look at the structure of the portable executable, if it's executable, a file type analyzer for PDFs and flash attachments. And then when we detonate it, we've got a bunch of things watching what happens. One of them is another great tool, Sysmon. How many people have heard of Sysmon? So that's a tool, the sysinternals tool that I wrote. I'll be giving a talk on that at RSA conference, by the way. I gave one last year, a big update to that. But Sysmon and ETW events, basically dynamically watching what this attachment does, if it's modifying registry keys, if it's creating files. We have API hooks. We see if there's crash dumps being generated. So a bunch of artifacts get spun off. It's like, the Hadron Collider. We watch what happens inside there, get traces of everything. And then there's a post-analysis phase as well, which is to apply the Yara rules. How many of you are familiar with Yara rules? I assume quite a few of you. So apply Yara rules to the execution traces to see if there's matches against any of the rule-based detections. If there's threat intelligence network to tell us if there's potentially in these patterns some malicious activity. Macro evidence that we see of the thing talking out to the network, network analysis, and so on. And all of this, then, like I said, we feed into those 2 machine learning algorithms. The fingerprint model we call one, and the behavior model is what we call the other one. So let's go into a little bit of detail about these 2 models. The first one, well, before I do that, here's what the data set looks like coming out of the detonation system. It's this log trace that's being compiled from all those different trace systems into one XML document that will have things like, there's a load image, it's process ID 2100, it's a W script, .exe. You can see the size of the image. You can see it's called some function here, create mutex. And so this is the kind of trace data that we feed into the machine learning algorithms. The first algorithm, the fingerprint model, we organize the data like this. We basically categorize it into different levels of granularity for each one of these events, where the deeper the level, the more specific it is. So you can see that first one, that row, process, load image. You can see that the user account system, well, that's less granular than a load image. It can be multiple accounts that might perform the same operation depending on the malware executing in different contexts. You can see that level 4 is it's an executable that it's loading as opposed to .bat or .dll. And then you can see level 5 is it's WScript. And so as we get deeper, the information gets more granular. What we don't want to do is overfit in machine learning, which means being too specific. So meaning that if we've got a rule or a machine learning algorithm that only looks and identifies malware based on the exact match of that line 1, then we're going to miss if any of those things change, which they will change because the attacker is being crafty and doing different things at different times. So we want to be general, but also learn from the specifics. So in this fingerprint model, what we do is we generate what are called n-grams. It's basically taking a look at windows of events, a sliding window of events of various depth and breadth. Now, this one example that I've got here, you can see that it's a depth of 8 and a breadth of 3. In this sliding window, we take those combination of features at each level, and we generate a hash from them. And basically, this is the fingerprint of that set of operations. And we slide the window forward, and we generate another hash there for that n-gram and another hash there. And for any one of these attachments that blow up, we'd probably 10,000 different n-grams we generate for a combination of about 1 million features that get spun off of the execution of one of these detonation chambers that get fed in to the machine learning algorithm, which then gets trained by real data, real label data, and looks for similarities across this n-gram. So when it sees a new trace come out of a system, and now it can go and process that and get matches against this, even matches when the malware is changed in very crafty ways because of the richness of all of the fingerprinting it's doing. It can still find, hey, you know what, it didn't do things in the exact same order, it did things with a different account or a different extension, but there's a match here, and it's a strong match because it's matched multiple n-grams. Now, the behavioral model is a little bit different. This one, we take, like I said, we take advantage of the static rules that we already have, the Yara rules, the static analysis that we've done, the matching of the Yara rules against the aggregates of data, as well, what register keys it opened, what files it accessed. And this model is attempting to detect new forms of malware. Again, based on similar ones that have been identified with the Yara rules. And then we take the combination of these two, and then that's what this slide shows us, is that we train this thing at regular intervals. There's about 270 gigabytes of data coming off our detonation chambers a day that we use for the training. And that training, again, at cloud scale is just completed in a few minutes. And then in the detonation chamber itself, what gets spun off is we do the classification. And that classifications of what comes off the detonation chamber just takes a few milliseconds. And it needs to be extremely fast because end users are waiting for their attachments to come through, waiting for this analysis. So we've got to be extremely fast on the analysis. You can see the true positive rate on Yara rules themselves of just about 82%. This is on a set of data at one point in time where we applied the Yara rules available to what was coming out of the detonation chamber, and about 82% was a true positive rate. We took that same set of data and applied it and trained to our trained algorithms, Model 1 plus Model 2, and we came up with 93.6%, a 10% improvement. I want to emphasize that this is just one sample set. This kind of highlights, though, the benefits of applying machine learning. There's advantages here to the machine learning algorithm. It's learning based on existing attack patterns, to identify new malware. And you have to remember, too, that this is applied only to those samples that made it through those 3 antivirus engines. So it's in the set of unknown malicious software, the true positive rate of about 94% off of what's left is what we're able to do on top of anti-malware using the system. And you can see the kind of action that's taken here, automated. So the end user gets this message as part of their email that says the attachment's been stripped. By the way, if you'd opened it, you would have been compromised. So a great example of taking data, label data, using it with machine learning in a creative way here of this detonation chamber, operating at scale in the cloud. We're launching tens of thousands, hundreds of thousands of virtual machine instances every single day And that number continues to grow as more customers on board to ATP to go and analyze their attachments for them and protect them from that zero-day malware. So those are a couple looks at the detection and automatic response and alertable, actionable response. Let's talk a little bit about the triage process, which security researchers have to go through, and how we can apply machine learning there. Then this is like very nascent steps that we're taking here. But I want to share it with you because, and I want to share all of this with you actually, because the Israeli cybersecurity community is one of the most advanced in the world. That's, Bharat mentioned, that's why we're so heavily invested as Microsoft here. This is space for the whole community to work on advancing. And so we think that by sharing what we're doing, we can maybe inspire you to think of creative ideas. I know there's a lot of startups in here, and you might come up with some advances that we could go and apply. In this case, what we want to do is help the security researcher. And the security researcher, the way we can help them is to not throw at them a bunch of alerts. Because alert one-offs, that is overwhelming, and that doesn't give them the big picture. Really, an alert, especially if you've got an attack underway, an attack is going to generate a ton of alerts all over the place. And the question for the responder is, which alerts are related to malicious activity? And how do I look at the big picture of what the attacker is doing? And of course, there's going to be alerts that are not malicious. How do I separate those from the true malicious alerts? And this is where we can apply some machine learning as well as some interactive tools for the researcher, which is what we're doing at Microsoft. Now, if you take a look at this, the way that we might visualize this is to categorize things into alerts and entities and nodes on a graph. If you think about a node, that's an operating system, it's a server. If you think about an entity, that's a user or a process. And if you think about an alert, that's, hey, this suspicious thing happened. And that's hopefully been trained well by machine learning to say this is likely a very suspicious thing. Again, false positives get through the system because the system is always being upgraded. And by the way, John Lambert, who's I mentioned here, going to talk tomorrow, he famously came up with the saying that attackers think in graphs, defenders think in lists. What we're trying to do is have defenders think in terms of graphs as well, because they need to do that to be able to compete with the attackers who are very graph-oriented. And this is a way of taking a look at potential attack data in a graphical form for a security defender. And so what you end up with when you take all those alerts being spun off a real system is graphs. Graphs that are connected through these different edges that connect the entities or the nodes together and with alerts. So an alert that connects two entities together, that connects a third entity together, suddenly you got a graph. And suddenly you can start to see the attacker moving around your system. Now what I'm going to show you is a demo of this tool in action with a real set of data that's come off of some of our internal systems. So here's the graph tool. You can see there's a whole ton of alerts and there's a bunch of graphs there. At this point, it's hard to determine where the subgraphs are. And so that's where this little columns over on the right side come into play. If I zoom in on that, you can see, looks like live zoom's not working. But you can see alerts, hosts, and entities. And just because something has a lot of alerts or something has a lot of hosts or entities or whatever, it doesn't necessarily mean it's malicious. Let me zoom in on one of these and show you what one might look like. In this case, we can see here's some nodes, bing.com, here's an IP address, here's a user, here's a domain, here's an alert, external web browsing, probably to this IP address by this user, and this coming off this machine right here. That's one example of what we consider an incident. There's a great cluster of related alerts and entities. Now here we see another one. There's 16 entities involved in this one, and with 6 hosts. So let's take a look at that one, and you can see that this one, there's a bunch of WMI activity across a whole bunch of systems. In this case, the researcher looks at, the responder looks at it and determines that this is probably not malicious. This is probably some management tool or utility running on that node and executing WMI commands across the other ones. May or may not be, but that probably doesn't look malicious because of the scope that it's operating at. But if we move to this top one here, there's a ton of alerts, a ton of entities, and a ton of hosts. And in fact, this is red team activity, labeled red team activity from Microsoft Red Team attacking us, labeled here, shows up in this, and now what the security responder wants to do is drill in and find out how to approach this. What are the nodes of interest? Where should I go and start my triage process and figure out what the red team's up to? One of the first things they can do is they can highlight all the nodes, all the entities. And this is applying machine learning, which is going to go and take those and weight them according to the number of connections to them from across the graph and highlight those ones that are maybe the ones that we should start with first because they're the most data rich. You can see that one pops out there, that lower left one. So let's go and zoom in on that. And this is something that the security researcher is able to do using this tool, is move around and highlight things. And you can see this is a SQL Server, looks like. And what they can do here is they can press H to hide everything but the activity coming off of that particular node directly. That gives them a scope view, so they get rid of all the other clutter while they're focusing on this. The second thing they can do right from this tool is switch to a tabular view of all of the alerts. So this gives them that next level of detail that might be hard to surface up in the graph. You press G to go back to the graph view. And now right from within this tool, we give them, or within this visualization, we give them the tools to respond to this. So they can right-click, for example, and reset the password on that machine. That might be the first thing that we want to do. It looks like this thing's been compromised, the password's been leaked, and so let's go reset it right now. But you can see there's a bunch of other things that we've added here, and this is a place that we're continuously evolving. But remember, what we want to do is make it so that anything that the security responder does makes it back into our machine learning algorithms. And what that means is labeling the data. So how do we get the responder to label this data right in place when they determine this thing, hey, this is malicious? Is that they can go and pop up a classifier right here and classify this as malicious and enter it in the system. And at this point now, that ends up being labeled data that we feed into the machine learning algorithms the next day. And then now, if the red team comes and performs similar type of operations, or a real attacker does, now we've got label data that will help us quickly identify with a higher degree of fidelity, this thing really looks like an attack, and very similar to the kind of attack we've seen before. Okay, let's switch back to the slides. So that's a kind of a brief look at how we're trying to push machine learning in Microsoft in cyber defense, with the mindset here that we want to disrupt the attackers with a framework of what we're looking for from our machine learning algorithms. Goal being, shorten the blue team's kill chain, stop the red team from getting all the way to its goals, or getting far enough on its way to its goals where they're causing damage. And here's some items that we look at for you yourself if you're going to go after this kind of disruptive approach by applying machine learning. One of the things is that you go collect data from different data sets. Be creative. That example of Office 365 labeled data to try to identify compromised virtual machines in Azure. You probably have other data sets that you're not thinking can intersect in ways to give you labels that you should look at. And develop scalable machine learning. Get your domain experts sitting alongside your data analysts, your machine learning experts, together to work on figuring out how to train the models, how to boost and deprioritize which algorithms to choose that best fit the goal that you're after. You can see we use different machine learning algorithms in different cases. Of course, you want a secured platform. Azure's a fantastic secured platform for you to do this stuff on. You need eyes on glass. You need to be having security responders responding to these things and labeling things like I showed you, so the easier you can make it for your responders to label the data. And this is one of the big problems in most organizations, is how do you get that labeled data? Like I said, we've got some unfair advantages at Microsoft with all the sources of labeled data that we got. But you've got your own sources of labeled data as well. If you don't have red teaming, apply red teaming to get labeled data. And then, just as a very minor kind of advertisement here for stuff that you can take advantage of in Azure. I talked about Azure Machine Learning as one of the platforms where you can go and play with algorithms. We've got sample data sets you can go play with, including breach data sets. You can go and play with different models, train the models, see what the outputs look like. It's a very interactive experience for that. And then Azure Event Hubs is just one of our hyperscale services for ingesting event data into a system that is going to be looking at anomalies. You might want to ingest that into something like Azure Data Lake or HD Insight platform to do big data analytics on top of it, or use R machine learning. Mentioned R, or you saw R back in that first slide, which is from Revolution Analytics, one of the companies we acquired that has machine learning algorithms and tools. So with that, I want to thank you very much. I hope you found this interesting. Again, this is, we're nowhere near done. This is kind of the first steps in taking machine learning as far as we can to really provide an automated, adaptable system for protecting our systems and disrupting the red team. So again, encourage you, if you've got ideas, let us know, and be interested to keep up with what you guys do on your own. With that, I want to thank you very much. I hope you have a great couple days here at BlueHat, and thanks for inviting me to speak to you this morning. Thanks.